Welcome everyone. Starting a little bit early, so I'll give 1 or 2 minutes for any of the others that signed up to hop in. Just share it on the screen here. And we'll let everyone know that the chat is open, so you can type any questions or comments into there. We have some moderators that can interact with you during the webinar. I'll try to get to questions at the end that weren't able to be answered. Feel free to put where you're located. Would love to see kind of the spread of those who are joining us. About 1 more minute here, and then we'll get started. Yeah, Stephen, I see you got a hand raised. If I'm not sure if you have ability to speak, but you can put any questions in the chat. There we go. Yeah, that might be what the question was. You see Sam said chat is working. There we go. All right, we got about 17 in. I think we had a pretty good number sign up, so wait a little bit longer. Did we get any stragglers in on this next 30 seconds? All right, we got one from Texas, of course. Texas speaking up. I love it. I have half my family lives down there, so love going down to visit their Longview area. And I'm a Michigan native, so look at that. We're based out of Pittsburgh here. Our headquarters are, but we have employees around. So, Nicholas, I have to ask right before we start: is that Upper Peninsula or Lower Peninsula? Got me intrigued now. Detroit, nice. Okay, so we're not too far. We're about 5-6 hours from you in the Pittsburgh area. I'm from the Upper Peninsula, so many times left off of the U.S. map, unfortunately, but it's still a beautiful area up there. All right, well, we're 2 minutes past, so we can get started. Thank you, everyone, for joining this webinar on the evolution of BESS cooling from air to immersion cooling. So if you see all the details on the screen here, I'll start advancing the slides and we'll get going. Again, questions, comment in the chat. If I see them as I'm going, happy to deviate into that, but Sam and EJ on our end will be able to answer any questions throughout. If we can't get to them, I'll get to them at the end. I'm John O'Newland, the Director of Business Development with EticaAG. EticaAG is a battery energy storage OEM that has designed and developed and focused development around immersion cooling. So very knowledgeable in this space, and we've worked with different engineering firms, architecture firms, just educating. That was kind of what birthed the idea of the bringing this course to the AIA. Energy storage is very popular now and getting deployed in a lot of different areas. I think there's a lot of misconceptions, especially around risk of energy storage for communities and even authorities having jurisdiction in those areas. So we're hoping to cover a lot in this in here today. So I'm not going to read all the course description, but essentially we want to look at from air-based cooling, moving into liquid cooling, then to immersion cooling, and how this impacts safety of batteries, performance of batteries, and just so you all can be knowledgeable as you're looking at any battery energy storage that you might be deploying within a project or might be interacting with. Just give you a little bit more warm and fuzzy on what are battery energy storage systems, the different chemistries, how those risks and performance metrics look, especially centered around cooling. It's a big key factor for the battery side. All right, so to cover the learning objectives. So first, we're going to identify the core differences between the air, liquid, and immersion cooling. Then we're going to look at trade-offs of each of the cooling methods. So again, fire safety, maintenance, energy density, and energy efficiency. So looking, again, these cooling methods for the different battery chemistries or the BESS that are deployed. Understand how evolving cooling technologies are reshaping best practices for the BESS placement in commercial buildings, and examine the connection between cooling systems and the BESS life cycle performance. the regulation side, very interesting side. We're dealing a lot with that as a company, but then the code compliance as well. So I know we have a big audience, kind of a wide audience. There's a lot of different compliances code-wise. We'll do what we can to answer any questions regarding that. But we will get into it. So these are the 4 main learning objectives that we're going to do. I did see the question on sharing the slide decks at the end. I believe we will be, but we can answer that more directly at the end through my coworkers. Yeah, we can. So EJ said we can. All right. So we'll get into it. So battery energy storage power. So these are common battery types used in energy storage. So lead acid had been dominant for many years. You have a pretty low cycle life in there, but really this matrix is showing where there's different chemistries that can be used for different applications. Right now, lithium-ion batteries is top of the charts for its availability, for its flexibility, for how it can be utilized and deployed. Though it does carry a high fire risk. It is one of the most energy dense that we have. It is most cost effective. And then it does offer the widest range of cycle life. And so just to clarify, lithium-ion is a pretty broad term. If you hear lithium-ion batteries, you can have different subsets, which we'll touch here as we go forward. But you could have NMC lithium-ion, you could have LFP lithium-ion, there's an LMO lithium-ion. There probably are some other ones that I'm not even mentioning here. But energy storage brings a very unique solution to the market, right? Power or energy is one of the only commodities that still needs to be produced as it is consumed. So storage, just like in food, right? A commodity that was produced that then would need to be consumed immediately or it would spoil. You got a refrigerator, you can now really change how you do food preparation and storage. And so really energy storage is doing that into the energy space. And so I know a lot of ways that these are being deployed with buildings and such. There are so many dynamic usages for energy storage. Not going to go into all of the different use cases, but again, focus mainly on what does the cooling system like? How does this impact performance-wise around the 2 main battery energy storage systems? So lithium-ion batteries, they are 90% of global grid battery storage market. So this is from the U.S. Department of Energy's 2019 report for a 4-hour energy storage system. Lithium-ion batteries are the best options when you consider cost, performance, calendar, and cycle life, and technology maturity. As I mentioned, everyone is looking for the new dense, available, cheap option for energy storage, but lithium-ion batteries have really taken the throne in this space because of all of those factors together, right? Sodium-ion is a promising one that might not have the risk profile of lithium-ion, but it doesn't have the availability as of now, right? With supply chain, the sodium-ion is based around sodium, which is very available. So there's so many things that go into why has lithium-ion become one of the main energy storage performers in the battery space. So we'll look a little at lithium-ion batteries here, the pros and cons. I'll only highlight a couple of these. Again, we'll have the slide deck available for you. But we have higher energy density. So that's important because you want to take up less footprint, but be able to produce the energy needed for whatever job or site requirement is there. So there's things such as flow batteries. Those can typically take up a large space. So we're always looking at site requirements. What do we need? We have what available space and what energy do we need to dispense for whatever project we have. So they are one of the higher energy dense batteries in the lithium-ion side. They have a long life cycle. So cycle life is really a charge and a discharge. So we're charging and discharging one time as one cycle. So how many cycles can we get out of this battery before it slowly degrades and is unusable? They have good efficiency, fast charging, discharging. So we don't want to wait around for EVs, right? 20 minutes at a charging station. We want to find ways that we can, similar to gas for cars, get in and out quicker. So there's properties there on the lithium-ion side. And then also lower maintenance. But on the con side, fire risk is one we'll sit on for a while as we go through this webinar, and thermal runaway. I'll touch a little bit on thermal runaway. We'll go in depth on it in the future, but really you have built up energy inside of the battery. And when that is released all at once through short circuiting or other methods internally in the cell, then that is going to just create a feedback loop that is going to spike temperature, cause super high heats to come out, and then that can actually trigger other ones into thermal runaway. So we'll dive into that deeper as we go on. But then it does have a little bit of higher cost per dollar per kilowatt hour is typically, if you're on the larger scale battery energy storage, that's where you're going to compare, trying to find a way to look apples to apples. If we're looking at storage in kilowatt hour or watt hour or megawatt hour, Those are what's our dollar per kilowatt hour is the main metric that we have. And then degradation over time. Lithium ion, it has good cycle life, but it does degrade over time. There's some chemistries that have very long cycle capabilities, much longer than lithium ion, though they don't carry all of those other metrics of availability and power output capability and density for site. So again, just really trying to familiarize everyone with the ecosystem of batteries, how they're deployed and how they're used. But we're just touching on this briefly as we're looking more on the cooling side and the evolution of cooling that came in. So one type of lithium-ion batteries is nickel manganese cobalt battery. So that does have cobalt is one of those materials that are hard to obtain, and it does provide a unique property for NMC batteries compared to, we'll get into LFP next. So this is ideal for fast charge discharge rates. So you'll find these in obviously machinery such as construction equipment, smartphones, laptops, and electric vehicles. So if we think a discharge rate is what's the capability that the energy I've stored, how fast can I put that energy out? And then how fast can I take energy in? So battery chemistries have different discharge or charge rates. It's called their C rate. And so you would typically have a higher C rate. Higher C means higher output or higher input that the cell itself can handle without being damaged. So NMCs have much better C rates that they're able to discharge or charge faster. That's why you find those in electric vehicles, because you have very quick response power demands, whether you're accelerating a vehicle or you're wanting to charge faster or slower. So on the safety metric, they are more prone to thermal runaway. So they trigger at a lower threshold of temperature to go into a thermal runaway, and they are a lot more volatile in their response to that. But we'll get into that in a second. On the performance, as I mentioned, higher power density. So they are more dense, one of the most dense lithium-ion chemistry types. For higher discharge in the charge rate. So again, we don't want a giant battery in a vehicle. We want a more compact battery pack that can discharge a lot or charge fast quickly. And these typically have around up to 5,000 charging discharging cycles. So the cycle life is up to 5,000. That's all going to depend, again, as we get into the cooling, on the environment. So how often am I charging and discharging this? How cold is it out? How warm is it out? The temperature is going to drastically impact the performance of these batteries on both the safety side, but then on how many cycle lives you'll be able to get out of these. And these are energy dense more so than LFP. So now I'll get on to the LFP piece. Lithium iron phosphate. So we have a lot more available material here with the iron side in this chemistry. And what this brings is it's slightly cheaper, it's less toxic than having the cobalt and the alternative of NMC, and it is seen in stationary energy storage. Some electric vehicles are pivoting to here, but really where we've seen LFP batteries shine is in the station energy storage. So one of the reasons this is because it is more safe than NMC, so its thermal stability is better. It's about 250 degrees Celsius is where the trigger point for thermal runaway is, where the NMC I didn't mention, but it's about 150 degrees Celsius. And typically with NMC thermal runaway, you'll get, if you've seen EV fires or even e-bike fires, that's a big issue. Those are a lot of the time NMC. That is, they engulf quickly. They have flame present when they go into thermal runaway because they have their own ignition source. LFP is more stable. They do off-gas some toxic flammable gases, but they are not as unstable as NMC. So for stationary, you're having larger quantities of it. So we wanted something stable that's not going to cause a big event if there is a thermal runaway. We want to be able to mitigate and maintain that, but more on that in a second. So the performance, you don't have as fast of discharging and charging is needed. Typically LFP, it can be higher than 1C, but what you find in the stationary energy storage market, so if say we're designing this into a building system with solar, maybe paired with a generator, a true microgrid where the battery is being dynamically used between the generator, the solar, discharging energy to the building for whatever load that is needed to support. So you'll find LFP batteries there more particular because you don't need as much energy storage. You have typically more space than in a compact EV car or on a bike. So weight and space are not as high of a constraint, and you get a much higher cycle life. So you're deploying batteries for longevity, or a lot more capital for a large load that you're trying to cover. So you want to make sure that lasts long. So these have 8,000 at like a 2-hour deployment. So for example, a 3 megawatt hour container could support 1.5 megawatts continuously for 2 hours, or it could do 750 kilowatts for 4 hours. So the 4-hour metric is going to affect how it degrades compared to the 2-hour metric. And so you could see 8,000 on a 2-hour metric, and then 10,000 discharge cycles and charge cycles on the 4-hour metric. So it is a little bit lower energy dense than NMC, though that is constantly evolving. I will say LFP has been deployed probably in the last 7 years, maybe even less. Don't quote me on that, but it has shifted mainly because of its cycle life, its availability with the iron phosphate. It's a little bit cheaper, so we can deploy more of it. Stationary doesn't matter about space and about weight as much as EVs do, or some of these other mobile options. So that is why LFP has become the predominant piece for stationary energy storage, especially on the safety side. So some critical challenges of BESS. So really 3 of these are related, and one of these is just the world we live in. So if we look at thermal runaway and fire risk, that is a key critical challenge with lithium-ion battery energy storage systems essentially at the forefront of that risk, because they carry the largest risk tolerance with risk profile of thermal runaway, with the majority of deployed, right? Again, we look back to the other slide, 90% of lithium-ion is pretty dominant in the battery energy storage space. And we don't want to have unreliable performance. So inconsistent temperature control leads to reduced battery life. So you get degradation depending on how you're utilizing it and depending on the environment it's deployed in. So that's something we're trying to always get better. How do we become more stable? How do we last longer and keep optimal temperature range and be able to allow these cells to perform better for their cycle life? Because that's our investment of deploying that. And now we're wanting to protect that investment. So the supply chain risk, as many markets right now are, but the battery space is interesting because China is fairly dominant in the battery manufacturing side. So I think in the top 10 battery manufacturers globally, China has 8 or 9 of the top 10 manufacturers. So CATL, BYD, EVE, they're building and manufacturing these cells, and they have a very fast R&D side of where they're developing newer and newer technologies. So a dependency has become directly on China, and then obviously we see within the governmental space of just how that's impacted supply chains, tariff exposure, and delays. So that's not necessarily related to these others, though it is a key factor that really impacts critical challenges within BESS. And then the project delays, this one is maybe some of you deal with predominantly, but you see community and AHJ pushbacks. They could stall projects due to safety concern with some of these lithium systems. So you find this in places such as California, in New York. There's moratoriums put in place by fire marshals because of community pushback, where they don't want to deploy any battery energy storage systems until there's better standards put in place for their specific locality. There are projects that have been AHJ approved for large-scale energy storage, and the community has shut it down in a vote, and now the developer couldn't launch that. So the project delays are directly linked to thermal runaway and fire risk. And a lot of this, unfortunately, is driven by the perception of batteries. When you have the small-scale batteries like an EV or e-bike, have many secondhand markets that then aren't stable, quality control's poor, and you see a lot of these micro fires that are taking place, especially in New York City, places like these in cities that are causing buildings to burn, fatalities. So small scale energy storage or small scale batteries, these are a big driver of the public perception. On the other hand, large scale energy storage, it has improved dramatically since 2012, which we have slides coming up on there, but I believe it's about 0.25% per gigawatt hour deployed is when the ratio of a fire that has occurred just historically from 2012 until today. But we'll get more into the fire side in a second here. So again, what is thermal runaway? This is a fire and a thermal runaway in BESS. So this is how it typically would happen. You have a single module that has many cells packed within that module. One cell, from many different reasons, and I'll show some statistics on where some of these fires occur, could be defective, could be improperly operated and run when it was overheated. maybe some of these system safety features have failed. So what happens is one cell goes into thermal runaway that causes the module to propagate all the touching cells and the neighboring cells. Now this module fails, then you get that spread to module failure, the enabling all the modules, and then it's eventually the entire rack. So again, it's a short circuit triggering inside where it overheats and it just creates this feedback loop. Yeah, I see, Eric, what you just mentioned on the large scale fire has happened in recent years. Yes, we have a couple slides on those. And what I wanted to emphasize with that 0.25% or say 1% per 4 gigawatt hours deployed, it has gotten more and more safe. But to your point, Eric, as a perfect point, that when a thermal runaway event happens, these are catastrophic events. They're not necessarily an e-bike fire, something that maybe can be contained or you have slight property damage loss, but there are catastrophic events that can have large scales go up into thermal runaway. So as I mentioned, these are kind of the EPRI or EPRI did this study from the root cause analysis of incidents since 2012. So this was the categories they broke them down into: design, manufacturing, integration, assembly, and operation. So really, with batteries, you always have to think lithium-ion batteries that there's potential for thermal runaway. So as you're looking at speccing and design of BESS, you have to be aware of the safety risks. Especially if it's NMC, that's a different risk profile than LFP. So just make sure you're aware of that. What are we sourcing? What are we trying to deploy into this project? And know the differences of the two chemistries. Now, these, interestingly enough, some of these fires have been caused by the cooling system. I know we haven't touched the cooling yet, but I really wanted to lay a groundwork for what is BESS, what are the different chemistries, what are the risk profiles of that, and then that's how cooling is going to impact in there. So batteries need cooling. This is a very intuitive point, but it is one that I think we don't necessarily, not everyone always thinks of the full impact of what cooling affects. So batteries, if they heat too quickly, right, you have the potential of thermal runaway, which we covered, but you also have performance. So if a battery is exposed to high heat, that is going to die quicker. We've all seen with our phones, right? If we are in a hot or cold environment, the phone can maybe start performing poorly, or the phone shuts down because it's left in the sun. That has happened to me. Or I've been in the winter up in the northern Michigan, and in the cold, the battery shuts down because it's not able to perform. So temperature management is key for batteries, and that only grows at scale. Batteries generate heat during operation, so that means that you're having a mass of cells that are generating heat. We need to deal with that cooling in some form or fashion. Worst case scenario, thermal runaway is triggered from that. And lesser scale, you have degradation is faster, so the longevity is going to die of that battery quicker, and then the performance also is going to be poor. So cooling is very necessary with batteries. So Eric, back to your point here. These are some more high-profile fires that have happened. There are more than this. I think there's about 26 fires at least recorded in some of the studies that I saw since 2012. And so we had one February 19th that is recent in 2025. Escondido fire. This was out in San Diego area, northern San Diego, in 2024. I was actually right the week after this fire. I was going to a battery conference in San Diego, so I was able to drive through Escondido and talk to some people who were involved with that. And one of the most infamous ones, one of the largest ones, is 300 megawatt hours system went up in Moss Landing in 2025. So these are recent. There was one in 2019 that really sparked concern about thermal runaway, not just with property being engulfed or losing some of these assets, but Surprise, Arizona is another that actually injured a firefighter who was not able to continue on the job afterwards because of the injuries. And that was a buildup of gases, and that actually exploded when he opened the door, threw him 30 feet into a fence. And so I've actually interacted with different firefighters who know of them, and so there's a lot of danger that comes at these large scale. I will get to your point saying that is a good question on the thermal management. EJ and Sam may be able to take that. So California's Moss Landing fire, look at the impacts of this. So Moss Landing power plant, this was actually an NMC batteries. This was an older system around 2014. It was deployed indoors, and you had one failure at a cell level, and that cascaded into a 300 megawatt hour burn. And so all of these smoke you see is not typical smoke that's of a normal fire. This is toxic and obviously flammable gases that are being put out into the air. And one big risk of this also is how do you put out fire? And firefighters spraying water on this, want to contain it, want to stop it from spreading. But now this water is taking those contaminants, putting it into the soil, putting it into any local water sources that it might be running off into. There are massive cleanup measures from a battery fire at this scale. If you see the metrics on the side here, 1,700 residents were evacuated in nearby towns. Nobody was injured in this one, but 40% of the batteries at the site were consumed by the fire. So you had like carbon monoxide, hydrogen fluoride, and these are some of the a few of the toxic gas outputs that were done there. So this was again an older system, deployed older. So there's still potential for these older systems to go. I think the metrics I've seen is actually the first year of deployment. That's where the risks are a little skew a little more toward because of quality control. If there was an issue of quality control, you might see that in the first year of operations. But that shows that there's still things that were deployed that we thought were safe at the time that we've gone away from. These were NMC, moved away from that to LFP. They were a lot closer together in spacing. We moved spacing apart and have different metrics around on the regulation side for this too. All right, now we're getting into BESS cooling types. And so how does cooling impact the battery energy storage performance, safety, all of these pieces? So we'll look at kind of the very first cooling that was deployed, what it's evolved to, and where it's at today. So air cooling, the very old faithful air cooling. It uses fans and HVAC systems that draw heat away from the batteries. So these are open racks, batteries there, cold air being blown across, and so you're able to draw the heat off of that. Now this is it's doable, but this is high cost, right? So we look at the pros and cons of air cooling. You have smaller initial capex. You can deploy air conditioning units relatively easily. You don't have some complex liquid cooling infrastructure as the other two may, the liquid and immersion cooling. Lower maintenance, you do have to maintain these air conditioners. Others may have different impacts or views of that on the low maintenance side, but it relatively is simple compared to these complex liquid systems. And it's a simple design for adaptability to harsh environments. But the cons, it's not well suited to large scale battery storage. And we'll look at that with some of these cooling metrics as we get into it. And then its performance is limited to the ambient temperature environment. So it's just not, it can't keep up enough with battery performance if you're in a very hot area, or if you're in very cold, it's just not able to keep that ambient temperature depending on your deployment area. The other type of cooling is liquid plate cooling. Now you may see this as liquid cooling as well. We add the adjective, and others do as well, plate, because it essentially is a plate that is placed underneath the battery cells, and it allows, in these veins here, you have liquid glycol running through that, just a standard heat transfer that's pulling through the metal plate, pulling the heat off the batteries, and the liquid is carrying that heat away to a heat exchanger, and then it is going. So this is what was deployed, first announced in 2020 by CATL. They brought this to the market, and it was deployed in the following years. So it has had a few years on the market, but interestingly enough, in those few years, this system was able to be retrofitted into a lot of old designs. And so liquid cooling, liquid plate cooling is now one of the main standards for cooling in battery energy storage systems. If you guys have been engaged with battery energy storage for some of your clients, or you've designed these systems in, typically you'll see liquid cooling it is in there. That means plates that have liquid running through them, the liquid is not touching the batteries. And I bring that up, and I'll show this video. With the pros, you have it's a matured technology. It's widely accepted, widely deployed. It has been only around for about 3 to 4 years at mass deployment, but it operates well under moderate loads with predictable thermal outputs. So it's definitely better controlled than the air cooled, right? We're just blowing cold air. Here we can circulate and we can draw the heat off. We have a little bit more control on how we can use that cooling. And it's compact and it's easy to integrate into space-constrained environments. We don't have to have these big aircon units blowing over the cells. We're able to fit those in. You have a heat exchanger, you have your pumps and whatnot to be able to move the liquid glycol. Some cons. So this does not prevent thermal runaway or suppress fire. So it controls temperature, but you can still have a cell that goes into thermal runaway. And actually, in that earlier slides from the causes, there's been, say, like for example, Tesla Megapack. I don't pick on Tesla. This is just, they published this report and EPRI had picked that up. But there was a liquid plate cooling leak that then got liquid glycol onto a bus bar that caused a short, that then caused a thermal runaway, that then caused a large-scale fire. By large scale, I mean into the containerized system. So this has been in multiple fires the cause of it, because you have a malfunction and a leak of the glycol that's running through here. So that is one of the main cons for sure, and relies on surface contact to draw heat. So it needs surface contact. Obviously, with thermal management, that is better than just air blowing, but it does not have the best efficiency with drawing heat off of this, and it struggles to keep up with thermal outputs in moments of high demand. So now we look at immersion cooling. Play this little graphic here. You see that liquid moving in there. So this concept is like data center and immersion cooling, as well as in transformers. We have the batteries are placed directly into liquid. Now this liquid isn't a liquid glycol that could cause a short as well. This is a dielectric liquid or a dielectric fluid, similar to put in, again, transformers or in data centers, that doesn't cause any short to happen. So as we look at immersion cooling, if I can advance slide here, there we go. So immersion cooling, you have the pros. It eliminates the fire risk from thermal runaway. Now this is key, and this is very interesting because we're talking about cooling, right? We're looking at performance of batteries, but what do we remember back to those constraints for the critical risks for BESS is AHJs and communities are worried about deploying these. So what immersion cooling does is it is, yes, the primary coolant mechanism for the battery cells, but additionally, it's always in place. As you see here, say a center rack, center cell goes into thermal runaway. What happens in an immersion cooling system? Well, what happens is that cell goes into thermal runaway. We can never stop a thermal runaway if it's an internal breakdown of the cell. Could be a quality issue, whatever it might be. But that goes into thermal runaway and it does propagate heat, but that heat is absorbed through the liquid. So now that heat is absorbed through the liquid, it doesn't transfer direct into those neighboring cells in the way it would without the liquid present. So this actually eliminates the thermal runaway propagation and the fire risk. Also, the cells are submerged into liquid, so that removes any ignition source from the cells, for example, NMC cells who carry their own ignition, or LFP that might have a short on a bus bar that could cause a spark that they could ignite the toxic and flammable gases. So we see that as a massive pro for immersion cooling. Then you look at extended battery life of the immersion cooling. This just makes logical sense, right? We have liquid touching the cells. It's drawing heat off the cells much more efficiently than one point of contact with a cold plate touching the cell. This is immersed, fully immersed, drawing heat. You could circulate that liquid out of those packs, having heat exchanger or whatever it might be, to do that. And then back to Eric's point, I believe, or someone else's point that I saw, in a cold environment, theoretically, right, we can add heat into the system, which they do. They put heat pads. With liquid cooled systems, they put heat pads on the cells to warm them up so they can keep the temperature of the cell at the level it needs to be to perform in a very cold environment. But with immersion cooling, we could now heat a tank, and the tank could be injecting the fluid in the correct temperature range that the cell needs to perform. So it really is dynamic in how it can be deployed. And it's stable thermal conditions under high loads and high demand. That this liquid stays in place. These esters that can be deployed in this space. That's really not. They're typically in transformers exposed to much higher heat. So this liquid is very stable in those high demand heat times of the batteries. It doesn't compare at all to where they've already been deployed in transformers. Then you also enhance lithium-ion performance. So because you have better cooling, as I mentioned before, you have a better life cycle. So a charge and a discharge. High heat causes degradation to happen quicker. And now with better thermal management, we're able to get better performance out of the batteries. So what about the cons? What cons is here? So additional weight with the added fluid inside each module. This is going to depend on deployment. What is my space and weight constraint of my job? A lot of the time with stationary energy storage, not necessarily an issue. But you're going to maybe find less dense solutions with immersion cooling than you could for large scale utility. Let's pack everything as tight as we can together. And so you might have a density comparison, a little bit lower energy density on one of these. Inherently, though, you're using the same cells. These cells are no different. The battery cells are the same in a liquid cooled or an air cooled. Again, China has some of the most large supply chain coming out of their country. So we're all using the same cells. It's how can we put this into a system that has good cooling metrics? And this also has a higher upfront cost. So you're going to be paying higher upfront costs. And one of the reasons is because you get full system redesign with immersion cooling. Liquid plate was unique that it could be added to previous, kind of grandfathered into previous designs. So it's easier to adapt and maybe say add $15 a kilowatt hour to add a liquid cooling system. Great, we have a metric, we can slap it on, it's good. With immersion cooling, we are fully redesigning down to the module level because we need to create modules that hold this. And this is a single phase. This is like an oil. So this is just liquid constantly in place, immersed, batteries submerged into that, so single phase. But it does currently carry higher upfront costs, but there's nothing inherently more expensive in this technology than in liquid plate cooling. The adoption is just so much more in liquid plate cooling, and you could grandfather it in or retrofit it into other systems. So it allowed liquid cooling to go a little bit quicker than the immersion cooling side. So a little higher upfront cost at this time. So here's some studies done of NMC modules with, again, higher C, so that's how fast I can charge and discharge. 2,000 test cycles were conducted on NMC. So this liquid versus immersion. So we'll just see in a performance metric, right? So in this test, we cycled that charge and a discharge as fast as we could to get it to 80% state of health. So your state of health is like, you can check all of these metrics on your phone battery. How much is my usable capacity now of that original 100%? 80% state of health is that terminology used to say I only have 80% left of this battery that is usable. That's the state of health. So we wanted to discharge and charge this because it slowly degrades as you use it to 80% state of health. We were able to achieve 1,500 cycles out of liquid cooling, but then we got 1,800 cycles out of immersion cooling, right? And this is a controlled test with NMC cells, and we were able to see, okay, we actually elongated the performance by about 22% in immersion cooling. So let's think about that in a system. Let's think about that in a system when deployed, right? So if liquid cooling is, say, at 10 years, again, state of health really can determine based on usage, environment, so let's not think of all the details around that. But if we see a 73% state of health at 10 years for liquid cooling, with this metric, we can see actually an elongation of cycle life by about 2 years, effectively gaining 2 years of performance on an immersion cooled system. And how about even further down at 15 years of liquid cooling, to get the same state of health, gain about a 5-year difference on that. I did see parasitic load from cooling and warming. We may have that come up. If that's coming up, I'm trying to remember if I covered that or was supposed to. If not, I'll get to that in a second, but I definitely see that. It's a great question on the parasitic load. All right, now we want to look at thermal runaway with immersion cooling. So again, air-cooled, liquid-cooled. We know liquid can cause some of those. Air is actually very dirty. It can cause particulates to build up, other things. So those don't necessarily deal with thermal runaway. But we have a unique system in immersion cooling where we deal with thermal runaway. So this was a test that we did with NMC cells, again, more volatile, trigger at about 150 degrees Celsius. Triggered a single cell, went into thermal runaway over 500 degrees. All neighboring cells that were immersed in this immersion cooling was below 100 degrees Celsius. So well below that trigger point. And that was all immediately adjacent cells to this. So we triggered one cell with a heat element, added heat into the system until that cell popped, went in, typically would carry a flame, but because it was immersed, it did not. And then we saw all of the neighboring cells were protected because the liquid absorbed the heat rapidly through the whole pack and didn't propagate immediately to the adjacent cells. So on the 20-cell thermal runaway test, this is a pack that has 5 kilowatt hours, so about 300 or so cells. These are 21,700 cells. It's like a giant AA battery, right? Cylindrical cell. You have about 300 of those into here. To get, for example, an EV has about 80 kilowatt hours. They'll use this cylindrical cells. This is 5 kilowatt hours, or an e-bike might be 2 kilowatt hours. So it's around a little double the size of an e-bike, right? If you've ever seen e-bike fires, those can get very large and consume very quickly into in a building. So here we triggered 20 cells at one time into this test. So this was before the thermal runaway. This was during the thermal runaway and after. All you see here, no flame present, but all you see at the peak was the gases being emitted out of the module, and there was no flame present throughout all 20 of these cells being triggered at one time. And in the aftermath, you had a very well intact system or module here that was able to contain that thermal runaway, allow it to run its course, and then allow that energy to dissipate, cool down, and then be inert. So with that 20 cell thermal runaway test, this is a schematic on the left side. And so we had 20 cells in the red, roughly 20 there marked, and then you can see on the right side the actual aftermath. So this was localized in the area where we triggered those thermal runaways, and all of the other cells are intact. This is with a static liquid. So this wasn't circulated in this testing. This is static. So these cells don't generate enough heat to need circulation based on the usages of this module. Though circulation would just increase its ability to exchange heat. So this was, again, static liquid that we're emphasizing the protection against thermal runaway risk. So it was localized into this area. I believe there was a row of propagation, but that's even more impressive that you might have got those initial cells that were next to those 20 to trigger, but it didn't cause a cascading event because the liquid was able to absorb. And if we look at that single cell, C1, that cell is in the center of all of these. I'll go to the next slide and highlight this. So the C1 cell hit 114 degrees at its peak. That is still below that 150 C threshold that we talked about. And now it actually had a positive voltage reading after the fact. So the cell that was in the center of all of those thermal runaways, the liquid dissipated the heat in the pack and absorbed it, and that it actually protected the center cell from even hitting into those dangerous temperatures. Obviously, any temperature exposure for cells might affect performance in the future, but the key is how do we mitigate and maintain any thermal runaway from propagating out. So who is immersion cooling benefits today? So there's benefits on both sides. Better cooling means better performance, means longer longevity, and better ROI for large-scale utilities, right? Or data centers using this to protect and manage their infrastructure. We don't want to have high risk be deployed inside of buildings that could carry a thermal runaway risk. So you have better performance, but then you have better safety that is brought up as we see this evolution of cooling. Air-cooled to liquid plate cooling to immersion-cooled. So these benefits impact all of these. We typically say critical infrastructure and dense populated areas is where you're seeing the pushback happen from communities or AHJs. Or you're going to be near high-risk environments that we don't want to lose property or personnel. And so that's where immersion cooling on the safety side might emphasize. On the other hand, you might be out in the middle of the desert and we don't care necessarily about the fire risk, though we have better heat transfer with immersion cooling. We have better performance. We could get better ROIs off of our system that might be front of the meter, doing arbitrage, doing frequency regulation, whatever those deployments might be. So this really impacts a lot of, at the very front end with immersion cooling benefits of the fire side, critical infrastructure, dense populated areas, but even on the performance side at large scale, you will see that starting to come in frame more for all of these deployments. Really, I think that what's the biggest hurdle for immersion cooling is going to be is that it needs a module redesign to be able to have that compared to liquid plate cooling. So, but it brings in a host more benefits of already what's dominant in lithium-ion batteries. It reduces the risk profile and increases the performance. Any technology that can do that for something that's so widely adopted will be adopted in time, unless, of course, another battery chemistry comes out, but there is no point of anything dethroning lithium-ion in the short term, especially over the next 5 to 10 years. So again, I just wanted to re-emphasize the learning objectives. So we identified the core differences between air-cooled, liquid-cooled, and immersion-cooled in BESS use case. So how are we taking that to our projects, right? So we're looking, is it NMC? Is it LFP? What's the chemistry needed here? That might be very basic level knowledge for you guys, but that's key for the performance on the cooling side. And then what type of cooling does it have? Air-cooled, liquid-cooled, or immersion-cooled? What type of job am I doing? Is this going to be out in the middle of nowhere? We want the cheapest product. Okay, air-cooled is probably going to be lower CapEx up front. We want liquid cooling because it's the standard of cooling in the market. We can get that, but we need to know the risks of how it could cause or it doesn't prevent thermal runaway. Or where is this location? Next to schools, next to critical infrastructure, next to personnel or residential units. We want to look at maybe immersion cooling as a better fit here where we can get over HJ approval and community pushback. We have that at our fingertips. So we looked at that. We evaluated the trade-offs of each cooling method in terms of the energy efficiency. We looked at the fire safety, the maintenance energy density. And then number 3 was understood how evolving cooling technologies are reshaping those best practices for the best placement in commercial buildings. And then we looked at the connection between cooling system, best life cycle, performance, safety, regulation, code compliance. I will go into, I see a pool of questions in here. Let me look through some of these that were at the end that Sam and AJ might not have been able to get to. Parasitic load, Sam did see, so you can look at what we found is because that parasitic load is much less, because you're increasing the thermal footprint of the cells, it's absorbing the heat. Now, even with air cooling on top of that, you can exchange the heat effectively, or you add in a heat exchanger. We don't have to circulate that as often because the liquid's absorbing it and it's keeping those cells at the core better compared to liquid plate cooling. We have to circulate at all times. So we have a better parasitic load or auxiliary power draw off of immersion cooled systems. And so even though you might have higher CapEx, your OpEx is going to be, you have to always consider what is my operational expense here. Parasitic load, great question. The longevity of this, as well as maintenance, where this liquid, these synthetic esters, the other things being deployed, that liquid doesn't need to be touched over the life of the battery. Whereas liquid plate cooling, you have a lot more leaks pose a higher risk than leak of an immersion cooled system. So there's always secondary containment, other things you need to look at, which are easily addressed. But power consumed by equipment used in cooling or warming, not necessarily for the actual battery itself. All right, I'm trying to see statement there. Sorry, I'm just trying to hit some of these that I can get quickly, and then. So cooling solution currently, yeah, I'll get into that right after the questions. That's a great one, but I'm just looking for the AIA portion of this. So liquid cooling uses reduction of overall water usage.
Hi, a good questions. Hey, thank you for the seminar, by the way. It's great.
Yeah.
So yeah, I mean, I can understand the liquid cooling, you know, you may not use as much as like the conventional cooling, like you use a kind of HVAC or something like that, because of liquid, they have better density. But then, you know, what if, like I'm in Minneapolis, right, Minnesota, and it's
Yes.
cold, right?
Right.
So you
Right.
don't need too much of that, worry about it when it's in the cold. But of course, now it's a lithium ion, so I understand there's a limitation on the charging
cold
side
side.
of it, right?
Yeah.
So
Yes.
now, I mean, the parasitic load I'm worried about, not just for the cooling, but also for warming. As you
heating,
can
right.
see, EV car, they use its own battery, that's not driving it, but to cool it so that it can charge. So that is also another major parasitic load. And I'm curious to see what are the typical parasitic loads that you guys see in the BESS system.
Yeah, on the
Thank you.
BESS side, for liquid cooling, we see about 5 megawatts per megawatt hour as a general rule of thumb. And then for immersion cooling, we would see about 5 kilowatts per megawatt hour. I misspoke there. 5 kilowatts of continuous draw per megawatt hour for liquid plate cooling. Immersion cooling, what we found is about 2 kilowatts per megawatt hour. But those, I think we're still in the early design phases of immersion cooling as well, to where what's really drawn people there is toward the fire risks, but the thermal management, I think, can still be utilized in better ways, to your point or someone's point, of adding heat into the system. I think of it almost, if we have any chefs out there using a sous vide, right? You cook a meat at a very specific temperature, and this heating element keeps the liquid at a certain temperature. That's essentially what you're doing with the batteries. Let's keep that temperature band as tight as we can. Even in cold environments, though, you could have, during operations, if you don't have proper cooling, those internal cells could start being exposed to different temperature variations, and they could start degrading. What's the problem if one cell degrades further than the other? Well, that's now the new capacity max of that module. So it's called state of charge. What's your state of charge? What's the capability of that? And if you get an imbalance in your system, now my system doesn't have usable energy as what it should if we had an even degradation across the board, which is one thing that immersion cooling can bring as well. So a great point. Cold environments, typically you can keep the ambient temperature of the container fine in a stationary cold environment. EVs are unique because they're mobile. You have different metrics with EVs. Stationary, we can control that temperature, ambient temperature of that deployment, unless we're in places such as the Arctic, which the Army is using a very different chemistry for those. But anywhere in the United States, deployed, there's batteries in all types of environments. And I don't have the parasitic load, though, draw for those different type of environments, because it really depends on how I'm utilizing that battery.
Right, but so if you what you just calculate or gave 5 kilowatts per megawatts there, so wait, kilowatts and megawatts, huh? So
Well,
that's
five kilowatt per megawatt hour of capacity.
right. So it's
Yep.
like a 5%.
Yes. Yep.
or 2% for the liquid cool. So that is very efficient. I mean, in a way, if you turn it to a PUE, that's a 1.02 or 1.03.
Right, right. And then, and not just for some of these deployments, people will do 300 megawatt hours, right? So now we're having that OpEx, your auxiliary draw is going to be fairly large as a part of just wanting to calculate. And that's why you want to just know there are different metrics. Key takeaway from this, different metrics from liquid plate cooling for immersion cooling for those OpEx. And that was kind of the key I wanted to drive in.
That's amazing. Thank you.
Yes. Yep. I see another question Sam was addressing there, but the coolant decreasing nearly 0.8 liters in that test. How long of time did it take? It was about 30 minutes. And also, can it be changed? The liquid could be changed in that module, but typically if batteries are being exposed to higher heat, we don't trust that they didn't degrade at some level. And so depending on your location, what system, your application, you might just remove those modules, replace with different modules. But that would have to be assessed. Again, a 1% chance of fire that typically goes into a large scale fire on a thermal runaway per 4 gigawatt hours deployed. If this were to happen, that's going to be not a regular occurrence that, oh, I had a thermal runaway, just go swap something out. But with immersion cooling, it mitigates that down, keeps it from going to that large spread, publicity, all these other things that it can protect from. So I don't want to think of a thermal runaway as always occurring in these large scale systems, but the potential of it happening could be devastating to wherever the deployment is. All right, well, that's all the questions here. So this concludes the AIA portion of the presentation. I can do a comment though, lifetime versus air-cooled BESS. Air-cooled is not as typically deployed. So I don't have metrics. Liquid has become the dominant one with LFP cells and stationary storage, just because it's much more efficient than air-cooled, and it's gotten cheap enough to be able to deploy with every system. So I don't know if you've seen air-cooled come across your desk or if you're looking to design one in. But we don't, even in the comparison chart that I had, the liquid versus immersion, air-cooled might be good for smaller deployments or indoor deployments, whatever it might be, where you can keep that ambient temperature of outside at a relative space. But so I'm sorry, I do not have metrics on that. All right, so that concludes the AIA portion. Real brief, we've covered everything in here. So at EticaAG, we do focus on the immersion technology. We designed it primarily for the fire safety side, but then the thermal management piece is also an emphasis of it, right? So we wanted to think through how do we have a safe, usable battery that can go where lithium-ion typically couldn't go. So we are a joint venture between a U.S. company, a company out of Taiwan, which the technology was developed and deployed. Now we're bringing this technology into the North American market, and so we're excited to be kind of dealing with that. But that also opens up a host of new issues with certifications and regulation that we're learning, and we're being the pioneer in that space on that side. But again, it's a already known technology of lithium-ion batteries. It's just an evolution of cooling. This is a good visual, and this is our product, how we designed it in, just to give you an idea of how this can be implemented. So this is our module. This has LFP cells, 20 cells in this particular design. And as this cutaway shows, all of the bus bars and all of the cells are submerged into that liquid. So that single container is filled with liquid. It's a liquid bath. And then in there, it's built into the racking system. We have a reservoir on the bottom that circulates additional liquid throughout. And then this first iteration, we have air cooled on top of this that just draws heat off of the aluminum castings by blowing the air over top. The heat, that's one reason why the auxiliary load is low with this. We essentially increase the thermal footprint enough to where batteries don't hit high temperatures typically. So we were able to just increase that thermal footprint and then air cool as one homogeneous mass compared to trying to hit each individual cell. Right now, everything is pretty even across the board. Then it protects against those thermal runaways as well. But many developments to come on how you can even optimize that thermal runaway piece. I do want to say that we've co-innovated this with Shell Lubricants. They're the liquid provider. This is a synthetic ester, environmentally friendly. That's key, right? We don't want something toxic that we're putting in place to solve one issue that causes others. So this is readily biodegradable, non-conductive. It has good cold weather performance, minus 50 degrees C pour point. It has high fire safety. I saw a video of where there's a pan of mineral oil and a pan of our lubricant, our cooling, and there was a torch torching the pan of mineral oil for 4 minutes, and then the mineral oil caught on fire. We did ours for over 70 minutes, and it still did not catch on fire. The synthetic ester has a very high flash point and fire point, and it is an organic material, so it is readily biodegradable. And then one last thing I wanted to finish out with, we think of batteries as layers of safety. Maybe I don't need to deal with gases that are emitted from a thermal runaway if it's out in the middle of nowhere. I can let those go out into the environment. But if I'm co-located with sensitive receptors or in a building potentially, even though we stop thermal runaway as a company at EticaAG with immersion technology from propagating to the neighboring cells, one problem that there still persists is the gases that are emitted. Now, we already reduced the amount of gases that are being emitted, but that is toxic and flammable. So a layer of safety that we have is called HazGuard. This is not a real life sizing even on here. It's just to give you an example of how this could be deployed. It could be deployed directly on top of a container. It could be deployed adjacent to multiple containers. We would vent gases through this, and this system, HazGuard, acts as a catalytic converter type system. That is, you're drawing a continuous flow and it scrubs and changes the chemistry of those gases, takes away the toxicity and the flammability. It effectively neutralizes those gases. So again, some people I've talked to called this the suspenders. We got the belt, now here's the suspender. So in some instances, this may be needed. This has been very interesting for Navy ships as well as our immersion technology, right? We don't want batteries in confined areas that could cause a lot of harm and damage, as well as the gases. So again, we think layers of safety. There's not one golden bullet or silver bullet to all. I don't know where golden bullet came from, but silver bullet to all of those. So we have to think, what do I need to deploy? What's the risks that I'm able to endure? And if not, we have these additional layers. So this is just a quick video that shows this is a battery that is going to be put in a thermal runaway with the gases being emitted and then filtered through the HazGuard system here. So you have sparkers up top that ignite the gases on the right. On the left, you have the sparkers going off, but the gases that are being emitted have been scrubbed of that toxicity and flammability. So that's just a practical way of seeing, oh yeah, I may still have gases in a thermal runaway, but if I need that to be captured and neutralized, there is that layer of safety that can be put in additionally. We didn't cover in the AIA portion, but that is kind of that safety suite that we provide as a company. Lastly, this is the footprints that we currently have, and we're getting more dense solutions coming by the end of next year, especially as we're looking at the FEOC question. We will have non-FEOC compliant and capable of ITC by Q4 of 2026, excuse me. So we are shifting domestic production here pretty rapidly while we have available production out of Taiwan for these footprints. And so 3 MWh in a 20-foot container. This is C&I product, again, for buildings, co-locations, what you might need, EV charging, pairing for peak shaving, whatever it might be. So it comes in DC blocks or an AC solution. We can provide this in the inverter side piece with you. This is a lower residential commercial unit. This one we haven't forced through into the US yet in the certification process, but that is also in line. Those are NMC cells. So again, thank you for those sticking around the last few minutes as we were kind of highlighting our company. So we have developed immersion technology in the battery space. Again, it was in data centers and in the transformer world. We brought that good technology in with the already established technology of lithium-ion batteries, lowering the risk profile but increasing the performance. And so I thank you for spending the time with us. The slides that have been put into the chat, and the domestic question thing, that is. We're using contract manufacturers for our initial on-ramp up in New York State as well as Pennsylvania. So we're headquartered out of Pittsburgh, Pennsylvania, though we have employees across the country, and that initial ramp up will be done in the state of New York. That will conclude the full webinar presentation. Again, thank you very much. You can follow us on LinkedIn. Sam put in the chat. Really appreciate the questions and the interaction and sitting through. I hope you gained a lot of value out of this. Feel free to connect with me on that QR code, reach out to me directly. I love talking about batteries. I have a hat, I should have brought it, that says I Heart Batteries. I got up in New York yesterday. So we're happy to help, happy to talk through and discuss this with you. And thank you all very much.